Today we're looking at a function problem from higher level. It says sketch the curve y equals negative absolute value of 5 over x minus 2 and the line y equals minus x minus 1 minus 4 on the same axes, clearly indicating any x and y intercepts and any asymptote. Well, the line is going to be fairly easy, so we'll just put our axes in here. We're going to cross. I can do better than that, surely. There we go, beautiful. Okay, so the line is going to cross at negative 4, and it looks like it has a gradient of minus 1. So we'll just sketch that in right there. This other function is going to be slightly more complex to graph, but the first thing I'm looking for is any asymptotes, because this is effectively a rational function. The asymptotes are going to happen basically for invalid x values. So I couldn't have an x value of 2 in this case, because then I would be dividing by 0. So I'm just going to put in the asymptote here. That's at 2. I'm going to call this x equals 2. And I'll mark this point as well, 0, minus 4. Yes, okay. Now, in terms of how this is going to behave around the asymptote, I want to think about what the end behavior of this function is going to be as we increase the value of x to very large numbers, or we go to very small, or I guess very big negative numbers, right? We go to like negative 1,000, stuff like that. What's going to happen for this function, since it's all on the bottom of a fraction, as we get very large, we're basically going to be dividing by very large numbers, and we're going to start approaching 0. The same thing is going to happen as we go to very extreme negative values. So my expectation is that we're going to be approaching 0 as we get towards the extremes. My expectation as well, since this is in the modulus, that means that any value that we have in here will be positive. It's going to be converted to a positive value, whether it's negative or positive to start out with. But then additionally, we're multiplying that by negative 1. That means every value should end up being negative, which is why I'm drawing the lines like this. And I would anticipate that we're going to get something that looks like this here. And then what I want to do is any x and y intercepts and any asymptotes. Okay, well, we're not going to have any x-intercepts for this value, for this function with the asymptote in it. But I probably want to see where this y value is going to, like where this y-intercept is going to happen. That's going to be at a value when x equals 0. So we would have something like 5 over negative 2 within a modulus minus, which just is going to end up being minus 5 over 2. So this point here, this point would be, let's see, x value of 0, y value of negative 5 over 2. And this is quite helpful, actually, because it gives me a sense of scale relative to the line. And I can see that I've done this probably a little bit incorrectly, right? Because negative 5 over 2, that's going to be smaller. That's going to be like closer to the x-axis than negative 4. So I want to kind of redraw this a little bit. So that's good as a kind of anchoring value. This curve should actually come in under here, and we should be crossing somewhere like here. So let me just sketch that in. So it's going to be something like this, and I'm expecting that this is then going to cross my y equals negative x minus 4. Right, I meant to draw the drag thing. Let's see if we can get that. Okay, let's just drag this up. Okay, yeah. And then I want this to be kind of symmetric. It's okay as it is, though, set up here. I'm just going to mark this as 0, minus 5 over 2. And then any other intersection points, it would probably be a good idea to mark the value here, which should be, given we've just got a minus 1, I'm expecting this to be minus 4, 0 at that point. Okay, and then we've marked all our asymptotes and we've graphed it. We're then finding any exact solutions to the equation x plus 4 equals 5 over x minus 2. Now this is interesting because this is, I'm just going to drag these over. These look very familiar to our lines, right? They're not exactly the same as our lines, right? But if we have these equal to each other, I think this is just an attempt to mislead us a little bit, right? Because what would end up happening if we multiply both sides by minus 1 entirely is we get something very similar to what we have set up here. So x plus 4 would be minus x minus 4. This would become minus 5 over the modulus of x minus 2. And this is identical because the modulus applied to just the positive 5 doesn't end up making a big difference. It's the x minus 2 part becoming positive that is the reason we've got the modulus lines here, or that's the difference that they make. So the fact that it's applied exclusively to the x minus 2 shouldn't really change anything. What we're looking for then are the intersection points between these two lines, basically. Now, have I done more setup than is necessary for this? Probably, because we're probably just solving this equation. But I thought it was important to draw attention to the fact that I think these are going to be the same intersection points. So how do we solve this? Well, like we often do with modulus, I'm going to look at a situation where x minus 2 is positive, and then I'm going to look at a situation where x minus 2 is negative. So if we have the values being positive, that's going to look like this, 5 over just x minus 2 as normal. And if I expand this out, we're going to get x squared plus 2x minus 8 equals 5. And then we're going to move the 5 over. 2x minus 13 equals 0. Now just double check this so I don't look completely silly. So x minus 2, we're multiplying that out. Plus 4 minus 2 in the middle gives us plus 2. Minus 8's here, we're equaling 5. Move that over, we do in fact get x squared plus 2x minus 13. I believe this is a calculator problem. Or no, I think this is non-calculator. Find the exact solution to this equation. Well, if we want an exact solution, I would either use quadratic formula, or we could do completing the square. And I'm kind of tempted by completing the square here because this looks quite nice. So x plus 1 squared would match up with our 2x in the middle, and then we'd have a 1 at the end. We want to get rid of that 1, so it becomes this. So we get sort of x plus 1 squared equals 14. We square root both sides. That's going to get us plus or minus root 14 minus 1. Okay. That seems like two solutions for x to me there. We are going to want to think about that a little bit more thoroughly, I think, because are both of those solutions necessarily going to make sense? And we also want to see, are we getting another two solutions when we look at the negative version? That will also be interesting. So I'm not sort of finalized on those yet. If we look then at our other version of this, it's going to be when we have basically negative values on the bottom. So the way we're going to simulate that is we're going to basically, the component that would be in modulus, we kind of multiply that by a minus, right? So it's now 2 minus x. And if we multiply this out, we get minus x squared plus 4x plus 2x minus this becomes minus 2x. And then we get plus 8. I'm going to double check all of that. And then this is still 5. So this would be from minus x times minus x, we get minus x squared. We would get 4x, negative 4x and plus 2x. So that gives us a minus 2x. We do in fact get a positive 8x. And then when I subtract this, I get minus x squared minus 2x. And this is going to be plus 3 equals 0, turning this into x squared plus 2x minus 3. Basically multiply everything out by a negative number. And then if we think about how to set this up, this is going to be like x minus 1x plus 3 would give us positive 2 in the middle. So we would have x solutions at 1 and x solutions at minus 3. Now those look quite compelling as solutions compared to what we're getting over here, don't they? So let's just think about this. Any asymptotes? I mean, both are theoretically plausible as x values and y values. Why are we getting 4 solutions? Well, I guess, we're also going to cross here, aren't we? I've completely neglected that. But we should only cross in one position, right? We shouldn't be crossing in 2 different places. What we're basically going to be flipping, right? We're going to be flipping along the x equals 2 line out here. So if we had, hypothetically, unmodulused values, right? So if we had what I imagine is our original equation, which probably looks something like this, then we would have had a solution here. And when you're taking a modulus, you've got to be careful that it can end up creating like phantom solutions that are beyond the value of the modulus. So just to give you an example of what this can look like, if we've got a function that's like, here, I'll do it with like a more standard V shape, right? When I do something like this, and we're looking for solutions where maybe it crosses a parabola like that, what's going to end up happening, this is a beautiful parabola, if I sort of have the parabola equation and I set it equal to the modulus and I consider the positive and negative solutions, it's probably going to give me a solution as if we continue down here as well, because I'm basically just solving it for two separate lines, right? I'm solving it as if we've got this line here and also as if we've got this line here that run all the way through. So in this scenario, I'm likely to get 4 solutions, even though there's actually only 2. So we need to be conscious of where solutions are actually going to occur so that we can exclude sort of false positives, basically, solutions that don't actually exist. And in this context, it doesn't make sense for us to have minus root 14 minus 1, because that solution ought to be floating, that solution ought to be floating out in the ether somewhere over here, right? And as we notice, like, there doesn't seem to be a solution there, but probably what's happening is we're imagining a version of the line that looks like this, and there would have been a solution here. And we're getting a solution for that, even though it doesn't sort of fit with the graph and the function that we actually have. So that would be the issue. It's a little bit weird, but if we're comfortable enough with the graph, like, this is probably why they're having us sketch it as well, is just so we've got a visual that makes it clear which of these solutions we're going to get.